Turbofan engines are a type of jet engine commonly used in commercial aviation and in some military aircraft too. They are designed to provide high thrust while maintaining fuel efficiency. Here's a detailed breakdown of how turbofan engines work. A turbofan engine consists of several key components. The fan is the large front component that draws in air. Then there's the compressor, which is a series of blades that compress the incoming air, increasing its pressure and temperature. Next is the combustor. It is the chamber where fuel is mixed with compressed air and ignited. The turbine extracts energy from the hot gases produced by combustion to drive the compressor and fan. Finally, the exhaust is where exhaust gases are expelled, producing thrust. Air enters the engine through the fan. A turbofan engine has a wide fan diameter compared to other jet engines, which results in a larger mass of air being moved. This design is aimed at optimizing fuel efficiency and reducing noise. Once the air passes through the fan, it enters the compressor section. The compressor consists of multiple stages of rotating and stationary blades. The rotating blades spin rapidly to accelerate the air, while the stationary blades slow the high-speed air to compress and increase its pressure. The compressed air rises in temperature, ready for combustion. The high-pressure, high-temperature air then flows into the combustor. Here's what happens. Fuel is injected into the combustor and mixed with the compressed air. This mixture is ignited, resulting in a rapid expansion of gases. The combustion process produces a high-pressure, high-temperature gas that expands rapidly. The expanding gases flow into the turbine section, where the turbine blades extract energy from the high-speed gas, causing the turbine to spin. This spinning motion powers the compressor and fan. In modern turbofans, the turbine is often connected to both the compressor and the fan. After passing through the turbine, the exhaust gases exit the engine. The key aspects of thrust generation in turbofans include the bypass ratio. Turbofans have a significant bypass ratio, meaning a large amount of air bypasses the core compressor and turbine. This design increases thrust efficiency and reduces specific fuel consumption. High bypass ratio engines are more fuel efficient, producing less noise. Exhaust velocity is also important. The high-speed exhaust gases exit the core of the engine, contributing to thrust alongside the bypassed air. The combination produces significant thrust, enabling the aircraft to fly. Turbofan engines are generally quieter than pure turbojet engines, since the bypassed air kind of acts as a sound barrier for the core noise. Their design actually allows for more efficient fuel combustion and better overall performance, especially at subsonic speeds. High bypass ratio engines are used predominantly in commercial aviation, where fuel efficiency and noise reduction are really prioritized. On the other hand, low bypass ratio engines are commonly found in military aircraft and some supersonic transports, providing more thrust and speed than high bypass engines. In summary, turbofan engines operate by drawing in air, compressing it, mixing it with fuel and igniting it, extracting energy to drive associated components, and finally expelling exhaust gases to produce thrust. This combination of features allows turbofans to be efficient, powerful, and relatively quiet, which is why they're the preferred choice in the commercial aviation industry. Basically, turbofan engines work by using a large fan at the front to suck in and accelerate a massive amount of air. This air is split so that a small portion goes into the engine core to be compressed, mixed with fuel, and combusted, while the majority actually bypasses the core. The core's hot gases drive the turbines and the fan, while the large volume of bypassed air, or bypass air, provides most of the engine's thrust, making it fuel efficient and quieter. This process is actually in 4 stages. 1. Intake and bypass. A large fan at the front draws in air. A small part of this air enters the core of the engine, while the rest flows around the outside in a bypass duct. 2. Compress and combust. The air entering the core is compressed by a series of compressors, then mixed with fuel and ignited in the combustion chamber. 3. Power the fan. The hot, expanding gases from combustion flow through turbines, which spin and power both the compressors and the large fan at the front via a shaft. 4. Exhaust and thrust. The bypassed air and the hot exhaust from the core exit through the nozzle. This high-velocity expulsion of air creates a forward thrust, pushing the aircraft forward according to Newton's third law of motion. The key features of a turbofan bypass ratio. This is the ratio of air that bypasses the core to the air that goes through it. Modern airliners use high bypass turbofans, 6:1 or higher, for high fuel efficiency, while fighter jets use low bypass turbofans for high speed and thrust. Noise reduction. The cooler, slower bypass air surrounds the hot, fast core exhaust, which helps to reduce noise emissions compared to a turbojet engine. Here are some notable fighter jets that utilize turbofan engines. F-22 Raptor, powered by two Pratt & Whitney F119 PW100 augmented turbofans, each delivering 35,000 pound force, 160 kN of thrust with afterburner. The F-22's engines feature thrust vectoring nozzles, enhancing its agility and maneuverability. Eurofighter Typhoon, equipped with two Eurojet EJ200 afterburning turbofans, each producing 20,200 pound force, 90 kN of thrust with afterburner. These engines provide exceptional performance, agility, and reliability. Sukhoi Su-35, powered by two Saturn AL-41F1S afterburning turbofans, each delivering 30,900 pound force, 142.2 kN of thrust with afterburner. The Su-35's engines feature three-dimensional thrust vectoring nozzles, enabling exceptional agility and aerial maneuvering. Chengdu J-20, powered by two Shenyang WS-10C afterburning turbofans, each producing around 33,000 pound force, 142 to 147 kN of thrust with afterburner. The J-20's engines enhance its maneuverability and acceleration capabilities. Dassault Rafale, equipped with two Snecma M88-4E turbofans, each delivering 17,000 pound force, 75 kN of thrust with afterburner. The M88 engines are designed for high efficiency, reliability, and reduced infrared signature. Sukhoi Su-57, expected to be powered by the new 177's fifth-generation turbofan engine, which delivers 14,500 kgf, 31,967 lbf of afterburning thrust and features advanced technologies like thrust vectoring nozzles and a full-authority digital engine control system. What's your take on the turbofan engine? Can it be relied upon in modern aviation?